I'm presenting Quack, a scalable remote measurement technique of application layer censorship. I'd like to thank my colleagues at the University of Michigan up here on the slide. So censorship is an oppressive policy of control of the information citizens have access to. It restricts people's ability to be informed members of their society. And while we usually think of big powers like Iran and China in this space, the technologies are actually spreading far beyond that because the technologies that enable censorship are getting much cheaper. And beyond that, the policies that are actually enacted are usually opaque, and this is to the benefit of the censors. It makes it difficult to have public discourse on the merits of the policy, and when they're opaque, the specifics of censorship can always be deferred to things that are lies and immoral. And so it's for that reason that we need censorship measurement techniques to be able to have a proper discussion about censorship. So censorship measurement techniques sort of began with what I'm calling anecdotal techniques. These are organizations primarily interested in public policy, like Freedom House, and they look at local experts in law, media, IT, academics, and they ask them questions about how expensive is it to get internet in your country? Do people practice self-censorship? What are government policies? And finally, what are the technical means introduced to enforce this? From here, techniques have emerged, such as OONI probe and the entire OONI framework that we heard about yesterday at FOCI. They get uniform measurement tools to volunteers in country to be studied to provide more concrete information to support these policy reports. However, recruiting, maintaining, and coordinating a large set of volunteers is challenging. So these techniques do not reflect the overall levels of censorship and traffic manipulation across time or at countrywide levels. And this has been requested by social scientists. So this is why remote censorship measurement techniques have been developed, and there's been a real surge in this area in the past few years in research. However, these techniques only focus on one measurement, one censorship technique at a time. So for example, we might consider DNS-based censorship or IP-based censorship, which both have remote measurement techniques, where a researcher in one country can perform measurements on other countries without owning servers in those countries. However, there's a third type of censorship measurement commonly associated with web-based censorship, the application layer. This is the hole that we plan to fill with our tool Quack, and you'll hear about the culmination of these three techniques at a lightning talk later tonight. So what exactly is application layer censorship? So here you have some person in country trying to make a GET request for a blocked website out of their country, and this necessarily passes the censor's deep packet inspection box. The censor sees the content of that request, parses it, or perhaps sees a keyword, and then injects some HTTP or error or reset to disrupt this flow. And even if the web server then can send the correct response, the person in the country being censored is not able to connect. So in order to detect this behavior, we can't just send some data. The green box is us in this case. We just can't send some data past the censor, because oftentimes they are directional in their blocking. This is a cheap and easy way for them to get 2 times the throughput on their censorship measurement techniques, because they can ignore half the traffic. So we identify what we call echo behavior. And by that we mean we need a server to be able to send us back arbitrary content, which then the sensor can react to, and we can observe a change in the TCP state. Now, there are a lot of protocols that actually offer this kind of thing. Think of the TLS heartbeat extension. And these protocols should be fairly familiar, except for one, perhaps, echo. So this is the entire RFC for the echo protocol. It was written in 1983 by John Postel, and it was written as a useful debugging and measurement tool for the transport layer. Any data received is sent back as a very quick and easy description of it, and it's on port 7. So it's a really simple instantiation of echo behavior, and this is great for us. However, it might be easy to disrupt with a port filter, but we're willing to go with this for now. And we observe about 50,000 of these echo servers on the internet today. So Now that we have echo behavior and an instantiation of it, what are the goals of the system we're going to design? We want to be able to detect which keywords are being blocked and where. We want to minimize risk to other people, in particular the echo server operators. We want our work to be robust to network failures. And finally, we want to make sure we have a design that can scale to very large network studies, an order of magnitude larger test list than prior works. So the shape of the way I'm going to describe this is from the inside out. We have a lot of layers of redundancy, so let's start at the inner layer and build outward from there. So let's look at this first step, what I call a trial. We have our measurement server on the left and an echo server on the right. We send it a request and it echoes it back. We then allow a 2-second delay to allow any race conditions in the network, allow the sensor's traffic to be injected and reach its destination, and then we test the TCP state of the stream. And if we get the correct string back, then we know that nothing's been interfered with, and we call that a success. Now I'm showing here the HTTP protocol is being tested, but this is just a choice because HTTP is commonly censored. You can use any application layer protocol here. So now let's build on top of that, build on top of those trials redundantly to form a test. So in this case, we want to test block.com. We first enter what we call the retry phase. We perform a trial for block.com. If it succeeds, we're pretty confident that it's not blocked. But if it fails, we want to keep retrying. We retry up to some tunable parameter number of times. Once it fails all of those times, we enter the control phase, where we take some innocuous domain, in our case we used example.com, and we try that. And if that trial succeeds, then we believe that the blocking was occurring due to the domain name. If that fails, then we enter what we call the delay phase. We sleep for 2 minutes. It turns out some DPI boxes will remember IP pairs, and it will block those IP pairs for some amount of time. We empirically determined 2 minutes was long enough to let these things reset, and more details about this are in the paper. And then we perform another control. And if that control works, we also determine it was blocked. But if that final control fails, we don't claim to have a result. And in fact, we throw out, if we keep seeing these non-results from a server, we throw out all of the data associated with it and throw out that server for this case, as it may have churned away or gone offline. So finally, we want to talk about the final step we perform for redundancy analysis, or in our analysis classification. So we want to avoid misclassifying censorship where there is none, and we don't want unreliable networks or highly local blocking to be misinterpreted as positives. So this lets our positives that we do show be more representative of national blocking. So for each country, we produce graphs that look something like this, where the y-axis is the number of domains that are blocked, and on the x-axis are the number of tests we saw blocking that domain. So country A here has almost no blocking on any domains, so clearly we don't believe there's any censorship here. Country B, on the other hand, has some, but they generally just trend downward, so we also don't call this censored. We think this might be due to some intermittent network failures in that country. Some countries are more unreliable in their internet than others. However, country C here has a very different shape. Some domains are blocked in many more places, so we mark those domains that are blocked in more places as censored. And country D also has this increase in some amount, but it doesn't have this zero space in between. So we use this is kind of the edge case of our heuristic, in which we say the point at which monotonic decreasing is broken is the point at which we start calling these domains censored. So this, combined with ignoring countries that have blocking only in one AS, is our heuristic. Later we'll discuss validating this heuristic against known things about internet censorship. And one thing I'd like to add is that more sophisticated statistical approaches here would be a wonderful contribution in future work. So before we begin sending packets, let's pause and consider the ethics of this work. There's a lot of incredibly beneficial knowledge that we can generate about deployed censorship. but there are potential risks for the echo server operators. They may face mistaken attribution from their government, and it's our duty as researchers to try and minimize those risks. So the type of questions we ask are, is the participation for the users voluntary, whether that be by us respecting blacklisting requests or using informed consent? If we don't use informed consent, is the risk no more than minimal? And finally, is the risk reasonable within the norms of the field? So we opted not to use informed consent for a variety of reasons. We believe that there's some risk inherent in communicating with outside censorship researchers, and there's also a risk of increased risk of reprisal if they're wittingly participating in censorship research rather than unwittingly. And we also believe that it may be infeasible at scale to actually contact, or infeasible at the scale that is beneficial as a contribution of this work to contact all echo server operators. But we do respect blacklist requests, and we believe our risk is minimal, and that's for a variety of reasons here. We only connect to our server, so the echo servers only connect to our measurement servers directly. That means they never connect out to the actual server that is the target of the censorship. And our servers are clearly denoted in several ways. We have reverse DNS lookups, whois lookups, and we run an explanatory web server on ours that all say that we're running measurement research. The connections are from port 7 on the echo server to our ephemeral port, and we send the first traffic and the SYN packet. The requests that we're sending actually have very different headers, so we don't send a user agent or any of these typical things you'd see in a browser. We just set the host header. And generally, echo servers are not user devices. However, it's possible a malicious government could interpret our measurements dangerously. So we suggest, as an additional protective measure, that future due diligence be taken to remove user devices from longitudinal measurements. And I'd like to add that we sought approval from our IRB, and they deemed our study was exempt as non-human subjects. So now that that's done, let's try and discover some echo servers. If you just scan the internet using ZMAP on port 7, you see about 5 million replies. This is good, but only about 57,000 of those will complete a trial with you. Most of those are just synacking on every port. And only 47,000 of those will still be there a day later. These are the set we use. These are in 34,000 ASs in 167 countries, so this is fairly good coverage. So once we have our echo servers, we'd like to identify them. Transport layer operating system detection could scale. However, it doesn't provide great insight into user device versus server because its classification is more on the kernel level, and kernels are shared. And so instead, we take a 1% sample and perform Nmap operating system detection. Now, these are the summaries of what we saw. 44% were servers, routers, or switches, but the more concerning fact is this one at the bottom, that 4% are non-server Windows machines and 2 were Android devices. We believe, due to our earlier arguments, that this doesn't preclude their use for our study. So now that we have some echo servers, we want to do a first demonstration of our technique. So we perform tests for HTTP blocking with this list of domains. So the Citizen Lab list is a hand-curated and labeled list of domains that are interesting in the context of internet censorship. It provides a good test to detect changes in public policy for many other techniques because of those techniques' limited capacities and the small size of the list. So we found blocking in the following countries. Only 20% of the roughly 1,000 domains on the list were actually blocked anywhere, and most of the domains that were blocked were only blocked in one country. Now, the most blocked domain was blocked in 5 of the 12 countries, but it was the only one to be so. And in particular, to break it down by these most popular categories, these are the countries that blocked news among its top domains. These ones blocked anonymization techniques, such as the Tor project's website, and these ones blocked pornography disproportionately. So in order to validate our technique, we compared the list of the countries on the past slide to policy documents that identify technical censorship deployments, particularly those of Freedom on the Net by Freedom House. We find it to be the case for all of those countries that we found those deployments, but that doesn't mean that we're actually observing all censoring countries. One example of this is Pakistan, who's known to deploy primarily DNS-based censorship. We're measuring application layer. We don't have a way to measure that. So next, let's demonstrate the flexibility of our technique. So our choice of HTTP was good, as HTTP is a common thing that's censored, but we can also measure HTTPS. Luckily, HTTPS connections are usually initiated with an extension that includes the domain name that you're connecting to. So we send this request, including that domain name for all of our lists. And of those original countries, only the bold ones here blocked HTTPS. Now, that doesn't mean those countries aren't blocked, that HTTPS is sufficient to circumvent in those countries. They could be using other blocking techniques. And something very interesting we saw that was anecdotally known before is that Iran actually increases its blocking by an order of magnitude in the number of domains when you start using HTTPS. So now we want to demonstrate the power of our technique to test large domain lists. So as we said before, the Citizen Lab list is good for detecting political changes, but it's hand curated. So that means it's very hard to establish some of the biases. So we want to demonstrate some insight that can be provided from the use of a larger domain set, the Alexa Top 100,000, which, while it's biased in its own right, has a different set of biases. So in order to perform this test, rather than performing a complete cross product of every domain against every server, we only test each domain 20 times in each country. And in order to perform this efficiently, we test only in the 40 countries with at least 100 servers. And this still took less than 3 days on one machine. So these are the countries we observed blocking in that test. We see over 3,000 more blocked domains when we do this. So this is a great source of new censored domains. Also, this list paints very different pictures of the amount of blocking in different countries. So there's an order of magnitude difference in the ratio of blocking in China to South Korea between the Citizen Lab test and our Alexa test. We'd also like to note that the number of domains that are only blocked in one country is also very high in this test, so that's interesting. And we discover a new category of censorship that we didn't see in our Citizen Lab experiments, shopping websites. And finally, there's another new interesting comparison we can make because of the ordered nature of the Alexa lists. They're ordered by popularity. So on the x-axis, you have the Alexa rank, and on the y-axis, you have a cumulative fraction of the domains. So sorry for the mess of colors here, but the blue line that's almost straight is Saudi Arabia. And because that's straight, we can say that among this set of rankings, Saudi Arabia seems to almost uniformly select from the rankings its domains that it blocks. Compare this with Turkey, the yellow line that is very curved. Their selection of blocked domains is very much weighted towards the top of the list, the most popular sites. So this gives us some more character into the blocking of these different countries. So finally, I'd like to talk about some of the limitations of our work. While we don't often consider ease of blocking in censorship measurement, it isn't circumvention work, we are even easier to block than other techniques. So a simple port filter would completely block echo servers. Further work can explore other protocols with echo behaviors to try and figure out a way to reduce this. Also, countries could be blocking based on who initiated the TCP connection or who sent the request first. We would have no way to detect this. And finally, we traded off a reduced granularity of observation for confidence in our results, and we also lost some coverage in doing that. Further research could apply more rigorous statistical techniques, such as logistic regression, to the classify step to improve it. So in conclusion, we demonstrate a technique to measure application layer censorship remotely. It can test more domains than prior work and can be combined with existing remote techniques to provide a comprehensive view of internet censorship. With that, I'll take any questions.
Hi. You mentioned you found a new class of censorship against shopping websites. And what I'm curious about is you explained how you distinguish between countrywide blocking and just a single AS doing some blocking. But how do you know that these shopping websites aren't themselves blocking users from these countries?
Yeah, so this kind of goes into the kind of recall back to the ethical argument that the connection is only between us and the echo server. So the actual websites that we're testing are not involved at any stage. So they're not receiving any requests, they're not sending any data. So it's actually, there's no possible way that they could be doing any blocking because they don't have anything to block.
Okay, thank you.
Bit of a follow-up to the previous question. Seems like it could be possible you're undercounting a lot of blocking. There's the point that Michael just pointed out, but also since all of your traffic's going over port 7, like any DPI box that's going to filter first on port 80 or 443 isn't going to see any of your traffic.
Yeah, so we did conduct some experiments where we actually spoofed our source port, or not spoofed, we set our source port to 80 and 443, and we saw no major qualitative differences between this. Given best common practices and the ethical concerns, we decided that it would be best to just follow the best common practices. And it's certainly true that we could be undercounting. That's kind of a deliberate trade-off we made for robustness. So we consider these sort of false positives as a much greater issue than false negatives. And so that's the kind of character that we're going for.
Is it also possible you're overcounting because between the measurement box and whatever echo server, there are other places besides the country to which you're attributing the blocking? That's not a real path between the client or the server. There could be other middle boxes that just block port 7.
Certainly. That's why we try and aggregate by country and only look for blocking that's spread across multiple ASs. So this will allow us to perhaps filter out, for example, in New Zealand, there were 2 echo servers that were both within a single college. And so their information on its own was actually able to make it look like there was censorship in that country. But because we could tell that they were within one AS and that the sort of nature of what they were blocking, we were able to make some judgments on that.
Cool, thanks. One final quick thing. Did you, the HTTP versus HTTPS was very interesting. You talked a lot about blocking. Did you see any manipulation in those things like downgrade attempts or other things with your client hello echoes?
We didn't dig into the actual contents. We just looked for any difference at all. That would be pretty interesting, and I believe our data will be public at some point. Go to the lightning session talk, and I'm sure there'll be more.
Thanks.
Thank you.
Hey, enjoyed the talk. Just real quick, you might have mentioned this in your slides before, but what was the reasoning behind the selection of the Echo protocol in particular instead of the other ones that exhibited similar behavior? I believe you mentioned like Telnet and some other ones.
Yeah, so the other protocols are kind of, the Echo behavior is buried either within extensions or in the case of FTP through anonymous read and write. So the Echo protocol is just a completely naive implementation of it, which is very convenient for us. That is probably the biggest issue. So it was so convenient to just send a request of some data and then have that immediately echoed back to us.
Thanks.
Thank you.
Yeah. Hi, thanks for the talk.
Yeah, thank you.
I was wondering what if you took some precautions to like validate that the echo servers or the backends that you were testing were indeed in the country that you thought they were to be, because one thing that we have noticed, for example, is that even for clients, GeoIP sort of resolution is not so great. And I would imagine it's even worse for like server-side infrastructure.
Yeah, so there are issues with geolocation. We kind of ignore this for our convenience. We believe that it will kind of come out in the wash as far as our redundancy goes. So the few that are misplaced will eventually just be a little bit of noise that goes away when we look at our heuristics. So thank you.
Thanks for the talk. It was great. So early on, you mentioned one of the things about OONI that was a limitation was that they have these volunteers who are running probes in country, and that requires a lot of sort of interaction with these people. Mm-hmm. Your approach also requires servers in country. You just don't control those. So you have some limit there on, like, in the long term, I think OONI is going to still be around, and probably your approach won't work. And I know you had this as future work, but could you say a little bit more about where you're going from here? Like, is your approach going to be, are you going to try to get it into OONI, for example, or, yeah, where are you going from here?
Yeah, so I definitely agree that OONI will continue to be around, probably longer than the Echo servers will. These techniques are a little bit orthogonal, where OONI has the ability to actually do deeper inspection. For example, at their keynote yesterday at FOCI, they looked at how far along the path the actual infrastructure was. That's something that we can't quite do with remote techniques. So the kind of immediate directions for future work, what we're doing is we're looking at combining these multiple perspectives, the auger, the satellite, and Quack, to kind of get a comprehensive view of perhaps web censorship as well as we can measure remotely.
Thanks.
Thank you.